Hello everyone, welcome back to another GIS mathematics lecture video, and in this lecture video I want to continue our discussion on map projections. And specifically I want to continue our discussion on the types or categories of map projections. So just to scroll up a little bit in our notes here, I just want to quickly review what we left off with last time, which was this idea of class, which described how we take the developable surface, which again, that's our 2D representation, and how we interact that with the reference globe, which is our 3D representation. And we said that class determines the shape, which is sort of the general way that we wrap the developable surface around the reference globe. And we said that there are three different types of shapes that are generally used. And we said that we can have a cylinder where we take it and we wrap it as like literally a can around the reference globe, and we end up with lines that are running north and south. They interact at 90 degrees and they're parallel. Then on the opposite of that, we have conic, where we made it like kind of like an old party hat that you would make as a little kid, and you set that on top of the reference globe, and you can see that we have the lines of longitude are straight and emanating from a point, and then the lines of latitude are curved, wrapping around the globe like that. And then for planar, right, we said that that would be just keeping the developable surface as a flat plane and simply resting it on the surface of the reference globe. And you can see that by doing that, right, we have, it kind of looks like a spider web, where we have the lines of longitude emanating from the point where the plane touched, out like the spokes of a wheel, and then we have the lines of latitude circling around it in concentric rings. So the next thing I want to do is I want to talk about the second aspect of the map projection, and that is going to be called case. And so in order to understand case, what we have to do is we have to understand the idea of tangent and secant. Now, I apologize because this is actually going to be a different definition of tangent and secant from what we talked about in trigonometry. So it's a little bit confusing here because we're going to be using trigonometry, but we're also defining tangent and secant in the context of map projections. So hopefully you can sort of keep that distinction. So case is basically talking about how many times does the developable surface touch the reference globe. That's the generic sort of broad definition of case. And there are two cases. There's tangent, where it touches once, and there is secant, where it touches twice. And so what I want to do is I want to draw a diagram explaining why this matters. So if you think about what we're trying to do conceptually, right, we're trying to take the three-dimensional reference globe, project the lines of latitude and longitude onto the 2D developable surface. And in a perfect world, right, in a world where, in the perfect universe, right, that would be a perfect projection, right? But as we'll see in the next video and when we start going through the math, that's not the case, right? There's always going to be what are called distortions. And so the reason that case matters is because there's only one place on a map. There's only one place on a map where we have no distortion. And that is directly where the developable surface touches the reference globe. And hopefully that makes intuitive sense, right? Because if you're trying to project something from the reference globe onto the developable surface, if they're already touching, you don't have to project, right? They're the same thing. And so what I want to do is I want to sort of diagram something out for you. So I want to talk about the tangent case, which is something that we kind of actually already talked about without really thinking about it. And I'm going to use the cylindrical class, right? So this is our reference globe right here, right? This is our developable surface, just like before. Okay. And so in this case, granted my drawing is a little bit off, right? We only touch the reference globe at the equator. I don't know if you can really see that, right? But we only touch the reference globe at the equator, right? That's where the developable surface touches the reference globe. So this red line, right? In the previous video, I called it the point of contact. Right. In this video, we're going to actually make it a little more technical, and we're actually going to call that what's called the standard line, which is, again, right, where the developable surface, which I'm going to call ds, touches the reference globe, which I'm going to call rg. And so because it only touches once, right, it only has one standard line, we call this the tangent case. Okay. And so you could imagine, right, there's really three scenarios, right? This is the case where it touches once because the diameter of the cone, or sorry, of the cylinder matches the diameter of the reference globe. You could imagine a case where maybe the diameter of the developable surface was actually larger than the diameter of the reference globe. And in that case, we would actually touch it 0 times. But you have to think about from the perspective of a map projection, that would mean that we would have more distortion, not less. So you will, I shouldn't say never, but it is highly unlikely that you will ever come across any sort of projection whose developable surface is not at least tangent, right? It is theoretically possible, but it will never happen because you'd be introducing more error rather than less. Because again, right, the standard line is no distortion. Right? That's what this means to be the standard line, right? Where the developable surface touches the reference globe, we have no distortion. That's the only place where we have no distortion. Everywhere else in the map, we have some form of distortion, which we'll talk about in later videos. So, just like we could, in theory, make the diameter of the developable surface larger than the reference globe, we can also make it smaller than the reference globe. So let's go ahead and look at what that would do. So if we have our reference globe again here, right, we have, so in this case, right, our diameter of our developable surface is actually going to be smaller than our reference globe, right? It's going to look something like this instead. Right, so now what we do is we actually have two different points of contact, right? One here. Granted, again, my drawing skills are not the greatest, but we'd have another one like down here, right? So in this case, right, we have two standard lines. Right, we have two standard lines. And again, right, standard lines are where the developable surface touches the reference globe and we have no distortion. So in this case, right, this is called the secant case. where the reference globe touches the developable surface in two places. Okay. And you could imagine the same thing for the conic case, where we simply made the party hat a little steeper, and so we pulled the bottom in closer, and we would actually intersect the reference globe in two places. Okay. So let's talk about from a perspective of what this actually means in terms of distortion. And again, we'll talk about the types of distortion in another video. But what I want to do is I want to draw this. Okay, so this right here is the curvature of the Earth. You could imagine it as if we were to cut off, right? You could imagine if we took our previous example here and we just cut a slab off, right? So in the tangent case, right, the developable, we'll use purple, let's be consistent here, right? In the tangent case, let me try and make this a little bit better. So this is our reference globe. In the tangent case, right, in the tangent case, we have, right, so the point of contact here would be going around, right? This would be going around. So if we have a point of latitude, we're going to put some random points, right? If we have a point here, a point here, a point here, and a point here, right? If we project them out, right, you can see right, this area here, right, because the reference globe is inside of the developable surface, right? We exaggerate the scale. So what this means is when the reference globe so let me think of a better way to say that. In the tangent case, in the tangent case, the scale is always exaggerated, except at the standard line. Okay, so hopefully that makes sense. When we have the tangent case, right, we have the standard line where there is no distortion, but then on both sides of the tangent, on both sides of the standard line, right, we exaggerate the scale. And again, you can imagine that because if we have, right, I'm going to do a terrible job at this, but if we have this is the center of our reference globe, right, and we're, you know, projecting out, right, that we've made whatever distortions that we're allowing are going to be larger than the real world, right? So this would mean, so put another way, when I say we exaggerate the scale, that means distortion will be larger than the real world, or than the reference globe, I should say. Okay, so that's the tangent case. Well, what about the secant case? let's do the same thing. Let's draw ourselves a reference globe here. So this is our reference globe, right? Again, we kind of cut it through a piece of it. And let's go ahead and draw our developable surface, cutting through it like we did before, but this time it cuts through it in two places. So we have a standard line right here, and we have a standard line right here. Okay? So now let's think about what happens. Right, so these areas, right, if we project, we're projecting beyond the reference globe to the developable surface. So these areas are going to be exaggerated. So again, any distortions are going to be bigger than what we have on the reference globe, right? But in this case right here, right, in this area, right, the developable surface is actually closer to the center than the reference globe. So in this case, right, any distortions here are going to be compressed. So these are going to be compressed relative to the reference globe. So this means that distortions are going to be smaller than the reference globe. So a way to sort of explain what I mean by exaggerated and compressed by larger and smaller would be to think of maybe the area of a country, or the area of a shape, right? If we do the tangent case, or if we are outside of the standard lines, where we're exaggerating the distortion, that would mean that the area of the object would be bigger than what we would calculate on the three-dimensional reference globe, right? Versus in this case, in the secant case, right, if we're in between the standard lines, we're in this area where the distortions are being compressed, that would actually mean that the area that we calculate would be smaller than the reference globe. Okay? I want to repeat this because it's very important. When I say that the distortions are going to be smaller than the reference globe, or that the distortions are being compressed, I'm not saying that we're making the distortions less important. What I'm saying is the distortions are actually going to be, I don't want to say negative because that's confusing, but exaggerated means, right, the area, if we use area as our example, the area is going to be bigger than we expect. When we compress the distortion, right, the area is going to be smaller than we expect, right? So again, exaggerated, larger than we expect, compressed, smaller than we expect. Hopefully that makes sense. I know this was a lot, but if you have any questions, please reach out. And thank you.